Welcome to Airbnb's Taking Flight. My name is Melan Shen. I'm a data scientist at Airbnb. I work in pricing, in a team under Marketplace. And I have been at Airbnb for about 1.5 years, really quick. So today, we are excited to have everyone here to discuss and hear about and talk about this topic about collaboration between engineering and data science together. It's always a question, how do the two different roles work together? How can we leverage the best expertise from different roles to make the most impact to the team? So without further ado, we will have all our speakers. We have a great lineup here with 6 talks. So we'll start the talks really soon, and hopefully to end the talks around 8. After which we will have a social and mingle time, so you can still stay here to hang out for a little while more. The talks will be about 10 to 15 minutes each. We have great topics from both Airbnb and other very interesting, exciting projects. So we will also push the questions to the end of all these talks. And give the audience time to ask questions to the speakers. Great. So the very first talk is from Junshuo Liao. She is a data scientist on search team at Airbnb. She received her master's degree in statistics from Columbia University. She joined Airbnb, so it's a fun fact. She joined Airbnb on her birthday in 2015. Let's welcome Junshuo.
Thank you. Okay. Today I'd like to talk about an example of how data scientists and engineers collaborated at Airbnb. As a data scientist, my work feeds on data loggings. And this is a real comment from an engineer from my team. And you can tell it how hungry I am for more data loggings. Engineers work with data scientists to implement data loggings while they build awesome product features. And this is a very common way for them to collaborate with each other. And today, I'd like to talk about a project that I've been working on and hope that can illustrate how this process looks like at Airbnb. So the story starts with some data loggings that implemented by the engineers, and it follows with the data analysis that I did. Sometimes the learnings from this analysis will directly propel some product improvement. But today, what I'd like to highlight in my case is how these learnings help the engineers and the team to understand our product better. And with the joint effort between the data scientists and engineers, we improve the data quality. And with the new data, we are able to build some metrics to help us to make better product decisions, and also unlock a lot of possibilities for future data research and product improvement. So let me quickly walk you through how a typical trip search journey looks like at Airbnb for the guests. So after users input their search queries, we'll provide a list of listings that we recommend on the search page. And they may select one of them to click into. And on the listing page, they can interact with the page by clicking on the photos. They can also check the host profile. They can also expand certain sections on the page or save it to their wish list for later search. And they may click into more listings until they narrow down to a few and make a contact and make a bookings at the end. So one of the mission of my team is to help each trip planner to find a unique match with the listing for their trip by providing more personalized and relevant content. To do that, we need to understand our user preference first. Do they like the search result we provided, or which one of them do they like the most, so that we can provide similar listings to them? Bookings and contacts are always very strong and explicit signals of liking a listing, but they are very sparse and take a long time to convert. Click-through rate on the search page can also be a good signal to have, but we think that we can get better signal if we can differentiate intentful or unintentful clicks by looking into the user actions on the listing page. So thanks to our engineers, we are able to log user engagement actions into data for analysis purposes. So whenever a user took an action on the listing page, we'll record it as a row in the event table, which can be easily queried through Hive or Presto by data scientists. And I also use an internal tool called Airflow to link and aggregate all these events together and aggregate them on a daily basis so that we can know how many clicks the users made, how far they scroll on the page, and how long they stay during a listing view. To link these actions to the actual user preferences, I built a machine learning model and use these as model features to predict whether this listing will be booked by the same users in the future. So the model performance was actually pretty good. So we can achieve AUC score at 84%, which means that if you randomly pick up a listing that be booked by the users and compared to another one that they viewed but not booked at the end, we are able to rank the booked ones higher than the other based on the model score 84% of the time. And the model also tells us that the total time users spend on the listing page is the strongest signal, and is followed by the scrolling depth. This chart can tell us how one feature influenced the booking likelihood at the end. The x-axis is the cumulative active time users spend on the page, and the y-axis is the normalized booking likelihood. As you can see that the longer the users stay on the page, the more likely they will book. And if a user can stay cumulatively longer than 1 minute on the listing, it means that they will very likely to book that. And also, the similar pattern can be found in the scrolling data. So we use the scrolling data as the percentage of page length that users scroll past. So you can see that the booking likelihood doesn't change much until they scroll past about 40% of the page, where we think is where the review section starts. So if a user has interest to read reviews, that's a strong indicator of liking a listing. So these findings are very interesting and can help the engineers and the team to translate those user engagement actions into actual user preferences. However, through the analysis, we also identified that there are some areas that we can further improve our data loggings. So for example, the scrolling data I just mentioned is logged as percentage of page length that the user scroll past. It's not directly linked to a specific listing section, such as reviews or map. So whenever there's a UI change in the future, that might lead to a totally different interpretation of the scrolling data. And also, besides from that, duration logging was logged as the total time users spend on the whole page. It would be nicer for us if we are able to know how long people spend on reading reviews or engage with the map. So I will talk about a nice, interesting application of that data logging later. And we don't have the duration and the scroll logged by the time this analysis was done. And we don't have a very consistent logging schema, which make the querying data a bit difficult. So we discussed these issues with the engineers, and they soon quickly jump on to some initiative to improve the data loggings, given that we know how important user engagement data is for us. So with a joint effort between data scientists and the engineers, data scientists spec the logging schema, engineers implement the code, we are now able to have duration and scrolling data on all platforms and slices by certain sections. We're also working on toward more consistent Gini schema logging. So with the new data, now search team can consider incorporate these as implicit user signals to improve our search ranking algorithm. And I'm happy to have more data to play with and be able to update my listing page engagement model. One interesting application is that we can have a new set of metrics to track how the distribution of user spend on certain part of the listing page changed during the experiment. That is super helpful for us because sometimes the product change is only limited to a certain part of the listings page. So we're eager to know how these product change can change user behavior. Previously, we relied on clicks metrics, but for the page sections that are not very interactive, it's hard to figure out. So with this new set of metrics, all the experiment running on the listing page can know how the product change affect the user behaviors and help us to make better decisions to improve our user experience. So to recap this story, I would like to say in this way, the data logging that were like the seed that planted by the engineers, data scientists take care of them and hope to harvest fruits from them one day. And the fruits can nourish the soil. So the next time when we plant more seeds, they will grow taller and stronger. So with this collaboration between the data scientist and the engineer, we hope to create a healthy data environment that help us to understand the needs from our users more and provide them with better product experience. And that's the end of my story. Thank you.
Thanks a lot. Oh, great. Okay, thanks for the great talk Jun gave us. Next is from June Andrews. She is a data scientist at Pinterest working on enabling data-driven products and insights. Previously, she worked as a technical lead of a consumer analytics and staff data scientist at LinkedIn, specializing in growth, engagement, and social network analysis. June's work connected the global and local effects between LinkedIn's professional network and individual members. She also worked on search algorithm at Yelp, created data analysis stack for Noom, a healthcare startup, and designed algorithms for computing the structure of large networks with John Hopcroft. June holds degrees in applied mathematics, computer science, and electrical engineering from UC Berkeley and Cornell. Welcome, June.
Thanks, Milan. Alrighty, okay. So don't worry, I'm not going to be teaching you electrical engineering and applied mathematics all the next 10 minutes. But we will be looking at data lakes and how to turn those data lakes into a data library. So to understand the order of magnitude, what data do we have to work with at Pinterest? Well, we have over 100 billion pins, and to put that in perspective, that means we've got over 13 pins on average per person in the world. So this is big data, and that data is being curated into 2 billion boards, which is users curating pins to understand how an idea can become reality. And that's being done by over 175 million monthly active users. And this entire data stack is amazingly supported by 400 engineers. So it's an incredible ratio of engineer to impact. It's big data. So what do we do with that data? In this one screenshot, we've got a variety of different data products going on. We've got search, where you can search this entire corpus. We've got category feeds. We've got, this is an SEO landing page. Given that you've landed on this page, we have related topics. If you click into the pins, then you have another data product, P2P. And if you click through into the sign up, then you have growth, which is also data-driven. So on this one page, we have at least 5 different teams working on data products that surface out to our users. And a lot of this has been built in the last couple of years. So they've been moving very quickly. And when you move quickly, your approach to data is for rapid development. And that's where data lakes come into play. Data lakes is a great way to move very quickly. It's the concept that I will take structured, unstructured, all the data I need, and I'll just put it into one spot, and then I'll build off of that. And so what happens is each one of those data products builds its own data lake. They build their own ecosystem where they have the data that they need, and they can move very rapidly from that. And that makes sense when you have small teams moving very quickly and trying out new ideas. The downside is that in these data lakes, you start to understand the cost of these data lakes because they're copying data from one central source and duplicating it in multiple places. So you can really feel that at the end of the month with your AWS bill when you think, okay, I really only need to store this much data, but I'm really storing 6 times that. Why is that? And that's because your data is being copied over to a bunch of different data lakes. The other aspect is that these data lakes are a self-contained ecosystem where people understand the data inside of it very well. And that works well when you have a team of 1 to 4 people, and it's okay to let the quality of your data be known as tribal knowledge, where you understand what data to access when is a matter of walking 5 feet to your left and asking someone. But as you grow as a company, that doesn't scale so well. 5 feet suddenly becomes, well, in our case, we've moved from 888 up to 651. So that's quite a bit of a walk if you want to go get some tribal knowledge. So you have a cost to these data lakes. They're great for developing very quickly, but you start to feel them as you scale. So where would you like to be? And that's where data libraries are amazing. Data libraries are the concept that can get you to the right data at the right time, and you don't need to care where it's at. So in a data library, we want the ability to understand what data we have across all of these data lakes, understand any additional details we need to know about it, and understand when I should be using it. So the process of then launching a new data product is not creating a new data ecosystem, getting all the data you need there, so much as leveraging the data that has been used in the past. Alrighty, so when the organizers asked me if I had any experience with managing collaborations between engineers and data scientists. Like, yeah, I can think of one project that has involved a bit of collaboration. When you're going from data lakes to data libraries, you're essentially changing your data culture. And that involved quite a bit of collaboration. The folks up on the right are the folks who contributed inside of the first 3 months. And this project has been going on for 9 months now and has reached a significant portion of the Pinterest data and ML engineer space. We've had over 50 engineers contribute to this shift from data lakes to data library. We've had over 7 managers help provide support on specific initiatives, over 5 PMs coordinating, and 3 of yours truly data scientists. So it's been a massive collaboration across the org and has fundamentally changed the data culture. So when you take on this large a project, it's great to take a step back and look at the philosophy that you want to approach this problem with. The technical aspects, they'll fall into place. The technical aspects are easy. But how do you approach something that's this large? And these were the key components that really helped us get traction and change what was happening. And the first tenet that we learned was that we were going to meet engineers, PMs, and data scientists where they were at. We were not going to make this a dictatorship of saying, you have to get over to a centralized data library, you have to do things this way. That was not going to fly. We would understand where they were. We would understand their problems, understand their bottlenecks, and understand how they were using data inside of each of their data lakes. So when you do that, you get a list of bottlenecks and ways in which your existing framework can help them. And that's great. Then you can immediately provide value in that collaboration. But the other thing is you're keeping your ear open for what are the next things you should be building out? What are the next things you should be incorporating into a platform that will help remove additional bottlenecks? And when you're working with these teams and you're bringing each data lake onto the data library, it's great to have a do-what-it-takes attitude. When you're bringing that many data lakes onto a data library, they're going to bottleneck at different places. Some are going to bottleneck at the PM stage of handling communications as they grow as a team. Some are going to bottleneck at the infrastructure stage. Some are going to bottleneck at the understanding what data they have to work with. And if you can take an approach that says, okay, whatever bottlenecks you're facing, we're going to handle, that'll remove any possibility of the data lake not getting onto the data library, and you can move forward. And when you're going through these learnings and you're providing value and you're building a more fleshed out system, it's great to take a path of least resistance. So we had a map of all the data lakes that existed, and these data lakes would be in different states. Some would be completely deprecated, where you could actually say, okay, we don't actually need the data over here. Let's go ahead and mark this for infrastructure to clean up at a later date. But data lakes have a life cycle to them. They have the initiation of when someone's trying to test out a new data product, and they have the mature point where this is a data product that really depends on this data lake, and some people will continue to develop products inside of that data lake. So it's great to understand where the engineers and the data lakes are in their life cycle and understand when are more opportune times to change how that cycle is happening and bring it into a centralized approach. And the last, okay, it slipped off the bottom of the slide, but there's two aspects that we really built out in this process that I would love to see in additional future large projects. And they're the positivity things. They're the things that build up your attitude. And on the positive build approach, it's really easy to go into one of these data lakes and say, why did you make that decision 3 years ago? Why didn't you spend an extra month making it into a more structured, maintainable environment? And it's easy to slip into that judgmental type of approach. But if you're judgmental, that is the fastest way to shut down a collaboration. And you have to take a step back and realize that the reason you're working with this data lake, the reason you're working with these legacy systems and tribal knowledge, is that there was something of value there that got you to the state that you're at today. And that value is something that's worth pulling forward. So take a look at what you have to work with, what is going well, and build off of the positive aspects you have to go forward. And the last aspect that I find it's really easy to get caught up in this momentum of finishing a project and then finishing another project, and you skip the most important step. And that is to take a step back and say, this person went out of their way to help make this project a success. They helped me in this way. That deserves a thank you. So there is an art to a thank you, and a thank you is an incredibly important part of the life cycle. There's no better way to begin your next collaboration than having known that your last collaboration ended on a positive note where you respected the work that you each brought to the table. So take the time to say thank you. So that's the philosophy. The rest of it's easy. You just have to lift a couple of mountains. So we took a hybrid methodology at this point. Pinterest was too big to go back in time and say, we're going to take a structured data approach. We're going to have data unit testing from the beginning. So we had to do a hybrid approach. We wanted to catalog all of the data we had and have a very shallow layer of understanding of all of our data. And so in this way, we created a lightweight platform where for each piece of data, each signal, we at least understood the English definition of what it was, non-trivial, the owners, and if possible, any current status of the calculation or health of that data. And the last part is that gets you a bird's eye view of what's happening, but then there are critical bits of data where it's important to go deep. So the lightweight platform. This is a short code snippet, and one of the things we realized when we were building this out was that a lot of data documentation is someone sitting down and writing out a wiki, writing out a document that says, I know where the best data is. And the problem with that is that it immediately goes out of date. That under the hood, someone changes a field, under the hood, they add a field, they delete a field, a workflow fails, and immediately that beautiful Google Drive or Wiki document that was really documented goes out of date. So we attached the documentation to the code. And we had a silver bullet, or an ace up our sleeve, that really helped here. And that was that most of Pinterest data was in thrift. And thrift requires you to declare a schema that says, I want this data to exist. So that's a great place to say, I want this data to exist. This is what that data is. Here is the owner, and here's the document that I will continually update as I learn more about this data. From there, you can systematically scrape that and link your documentation to your code. It's a small, minor detail that really helps you scale to hundreds of signals and hundreds of features. On top of that, we developed a really lightweight template for documenting signals. This is your, I need to know this inside of the first minute of finding new data. What is it? What is it about? Is it about a pin? Is it about a link? How is it related to other data I may have seen? When should I use it? Yes, I will admit this documentation goes out of date. So when was the last time this documentation was updated? Who owns it? Where is it located? And this helps you out at the end of the month. How much am I spending on this data? So that documentation linked with the code means that you can auto-generate a registry, and this scales to thousands of signals. So this is small wins that add up to huge breadth across a large chunk of data. The other side of that was going deep. Going deep is our favorite bit. Once you understand all of the data you have, you can understand, okay, I have 6 different gender models. Let me go ahead and compare them all and figure out what is the one gender model we should be using. And going deep, I'm not going to go deep into going deep because I think there's a lot of experts in this room, and this is our favorite part. By the time that we understand what the problem is we're trying to solve, there is a lot of documentation on how to do that. So after all of this, one of the reasons I think that data lakes are really popular is that we've given startups the conventional advice is that the only decision you cannot undo in the data realm is you cannot go back in time and record data that you were not recording. You can undo Hive, you can undo Spark, you can undo all of those things at a later date, but you cannot undo recording your data when it happens. And so these data lakes form under the idea that I will record everything in unstructured blobs potentially, so that I can go back and mine it at a later date. And I think I'm going to go back on that advice after having cleaned up one of these and give a bit of a revised wisdom that if you haven't created a mess, don't create a mess. And if you have a small mess at the Pinterest scale, then you can clean it up to some extent. But if you have a big mess, you're SOL, and you just have to sit on top of that mess. But not to forget the last point, is that when you're collaborating with engineers and data scientists, take the time to say thank you. At the end of each month, we would release a monthly newsletter that showed the highlights and thank the engineers for going above and beyond for helping in this process. And also shout out for how people could be involved in the future. And in that way, keep the collaboration cycle going of this being a very positive program that people could contribute to. And the other aspect of it is that once a month, I would go on and figure out what the most popular cupcake recipes were of that month and bring in a couple dozen cupcakes. So on that note, thank you so much for your attention, and feel free to reach out.
Thanks, June, for the great talk. I think everyone loves a data library versus something unorganized at all. And there are a lot of lessons we learned through this talk. Next, we will have Laura Kelly and Teresa Johnson from Airbnb. So now we have gone through the process of collecting data, organizing data. It's time for us to take a closer look of how to build products. Teresa Johnson is a data scientist on Homes 2.0 at Airbnb. She completed a PhD in aeronautics and astronautics at Stanford University before joining Airbnb in 2016. Laura Kelly is a software engineer on the vacation rentals team. She went to Washington University in St. Louis and studied cognitive neuroscience. She joined Airbnb in 2015. And here they are.
Thank you. So that was an amazing talk. Really amazing act to follow. But we are really excited to talk about the more specific details of actually building product, how engineers and data scientists work hand in hand to do that. So I've been at Airbnb for just about a year and a half, working on the supply side, and we've both been working on supply side growth over that time. So how many of you out there actually work specifically on a growth team at your company? Excellent, excellent. So we're really happy to talk about the best practices that we've learned for growth and experimentation and metrics, and how to drive those through engineering and data science collaboration. So first, what are the metrics that we use to track? We have a couple of metrics. We look at new homes added on the supply side. That is a home that's actually started the process of being listed on Airbnb. New homes published, which means they finished the process and are now searchable on Airbnb.com for guests to book.
And we also look at the home onboarding funnel, which means if a user starts listing their home on Airbnb, do they actually finish the whole process of listing it? And finally, we look at new homes booked, meaning once the user has listed their space on Airbnb, is that a home that guests actually want to book and want to use?
And so we move these metrics using experiments, and that's our primary focus for this data science and engineering collaboration. And so we, on the supply side at Airbnb, have to be very selective about which experiments we run. The plot at the top shows a power analysis for two of our key metrics, new homes booked and new homes published. And so power analysis is a method of determining the minimum effect we can detect with some statistical significance given a certain amount of power. And so on the x-axis, you can see the experiment duration, which is basically the number of samples, and on the right is the minimum detectable effect. So for some of you, 45 days might seem really short. For some of you, it might seem like an eternity. But for us, that's an eternity in engineering time. And given that it takes 45 days to see a 2 to 3% lift in our experiments, we need to be able to iterate rapidly. And so we have to be selective on which experiments we run and in what order. So we curate growth work through a very concrete planning process. We begin by looking at the logging data to identify, so I start by identifying places where users are having trouble by digging into the data. Then I will typically create an estimated impact from that problem area. So as an example, maybe the data shows that only 15% of users can successfully add a unicorn feature to their home to succeed, right? But if only 1% of listings ever even try to add a unicorn, that opportunity might not actually be that big. And so it's a big problem for those who want to add unicorns, but not a big problem for Airbnb in general.
And then once data science has informed us about the potential impact, we'll work together, the engineers and the data scientists, to define the potential, the user problem, the user experience, and brainstorm solutions. And then after that, the engineers will size the effort so we can balance the impact we have from a data science perspective with the impact it would take on engineering to build out different features. And then after that, we prioritize based on that information.
And so I'll just give you a little bit of a mental break. Here's some unicorns dancing. There's your joke, Vaughn.
All right, so once we've defined what experiment we want to run, how do we actually run that experiment? So first, to start off with, the engineers will go and build out the feature.
And then we'll work together to determine the experiment delivery conditions. So what actually triggers when this experiment gets delivered, and how do we ensure that we're not triggering it in a way that will create imbalances in our treatment and control groups?
Once we've figured out, the engineers go in and build the experiment delivery. So in other words, we build out the part that assigns a user a different condition, control, or treatment.
And then I'll go in and write code to create and track the key metrics. And so here's an example of those key metrics. What I'm showing here is a partial screenshot of our internal tool called the Experiment Reporting Framework to easily keep track of our experimental impact on hundreds of metrics at once. So on the left, you can see percentage change, In the middle, there's p-value, which is the probability that the percent change could still occur if the null hypothesis is true. And on the right, we have minimum detectable effect. And you can see in percent change, there are metrics that turn red, metrics that turn green, and often what data scientists have to do is dive deeper to assess these trade-offs and actually decide which treatment to launch.
All right, so now we're going to talk about experiments that we've run on homes onboarding. So how do you add a home onto Airbnb? So the steps are, first you add some basic information such as your property type, number of bedrooms and bathrooms, et cetera. And then the host adds some information about upsells, things like pictures, descriptions and features, things that would entice guests to book their place. And then finally, they add the calendar, price, and house rules. So when we first started thinking about experimenting on this, the steps could be done by a user in any order they wanted. But then we switched to a model where hosts would be guided through a series of linear steps so we could provide more information about each step. And this was difficult from an engineering perspective because there's a lot of state that we have to keep track of what is the user completed, have they filled out all the fields that are required, did they skip an optional step, et cetera. And so then we worked on logging when we launched this new flow so that we could figure out later on what we wanted to experiment on. So before we launched this flow, we worked closely with data science to figure out what we should log. So we ended up logging impressions on pages, clicks, step completion in prior projects. And we did this by building a utility in JavaScript that would log also all sorts of step information, timestamps, so we would know exactly when and how people were completing the steps.
And so data science helped design this logging to really give us a new way of visualizing and understanding the onboarding process, because now we can look at it as a funnel, as opposed to just disparate steps. We can look at funnel statistics around conversion from beginning end to end, specific step conversion. And when I looked at this funnel, when we first launched this, I found multiple drop-off points that we could iterate and drive improvements on. And so the first I'll talk about here is the upsell step. So you'll notice here that there was an 18% drop-off on the upsell step. And when I dug in further, we decided to focus on the description step.
So this description step, we knew from qualitative user research that guests would spend a lot of time on this step. They would have a blank page for a while, then they would write something, and then they would revise it. So we thought hosts really need help filling out this step. So the first solution we tried was we made a description builder where users could click tags that data scientists had picked from our guidebooks, and we would build a sentence for them about those tags that they clicked on.
And so, we'd use these tags to auto-complete the sentences and fill in the description. Unfortunately, this highlights-based approach was actually hurting reservations for the new homes that used this feature. What happened was that it increased step completion. However, it actually created cookie-cutter descriptions, so they weren't getting booked as often compared to their counterparts that had more flowery descriptions with different structures. So the data science challenges in resolving this were using learning to find more specific tags that actually would help hosts complete the flow, but are still appealing to guests. So guests didn't want to read the same sentence structure over and over again, but how can we make the step easier for hosts so that they don't have to write endlessly? And I also had to model how likely they are to get booked versus the description length to find the best word limit to enforce if we were going to allow them to write something on their own.
And from an engineering perspective, it was quite difficult to build out this description builder because it was writing sentences, and as a global product that's used by a lot of hosts in different countries, we had to make it work with a lot of different languages. So we had to think about the trade-offs of what's the best user experience versus how much time we had put into building that component and taking that risk. So what we eventually ended up working on, what we eventually arrived with after experimenting is a much more conventional, just regular text box. But instead of having a tag description builder, we had checkboxes with fields that data science had found would most be appealing for a listing. And users could check off that checkbox.
And we also found that a 500-word limit was the most productive, both for step completion and for eventually leading to a booking. And The result of this more simple but effective solution was a 2.1% increase on new homes booked. So this was actually a very successful experiment, simple but effective. So again, going back to the onboarding funnel to continually identify new places where we can improve, I then looked at the advertising step and found a 25% drop-off from starting to finishing the advertising step. Now this is just basic information. It's bedrooms, it's bathrooms. How could that be? Well, when I dug in, I found that the location step was particularly problematic.
So you would think that this step would be pretty straightforward, right? You enter in your address. But it's actually a pretty personal thing to be asking right off the bat. And we also found that in certain markets, such as rural areas or vacation markets, dragging the pin to the correct area could actually be very difficult if we don't have the correct, if it doesn't autocomplete with Google Maps correctly. So it actually is kind of an involved step.
And so the location step accounted for nearly all of the drop-off from that advertised section. And the data science challenges in sort of righting the ship were one, to deep dive to determine the percentage of users that were actually suffering from Google Maps errors. You can imagine our logging was quite good, but it wasn't as deep as we needed. So finding out how those errors were happening and how often they were happening was very challenging. And then also modeling the expected conversion on the new step placement, given moving it to multiple steps. So if the problem was that the step just occurred too soon and people weren't ready to provide that much personal detail, I had to model where is the best place to put it, both for conversion and for eventually finishing the flow overall.
And the engineering challenges with this is that, first of all, we had to build the flow so that you could move steps around depending on which experimental condition the user is in. And also, we have a lot of onboarding, such as emails that are tied to unfinished listings that assume that there's a location associated with that. So we had to both create the listing wherever the location step was placed, but also keep track of what the user does before those steps if we move the location step.
So we eventually moved it back a few steps, about 3 steps, to the 4th step instead of the 1st. And this really small change actually resulted in a 2.4% increase in new homes added. So that's actually the number of new homes that have been added to our platform. And so that was actually really huge. So here's some best practices for a successful data science and engineering collaboration.
So first of all, communication between engineers and data scientists is really key. We communicated really well about the logging before we launched this experiment. So that way we could go back and figure out exactly where we could improve things. And also define your expectations and success with regard to metrics. So that way you know what you're trying to go for.
It's also really important to trust each other and leverage complementary skills. It's possible that I could go in and learn how to, write the logging myself, and she can certainly start querying data, but that's not very efficient. So we have to be strategic and use our trust in each other's complementary skills to be able to hand off tasks and know that your counterpart will be able to execute on them flawlessly.
And finally, brainstorm together. Data science knows about the impact of different kinds of features, and engineers know about how much it would take to build certain features. So you can leverage each other's knowledge and brainstorm together to come up with a good solution that balances both things.
And you can also use asynchronous tools. This is pro tip: use asynchronous tools like docs, wikis, other types of communication media to avoid meeting overload, because we're all scientists and engineers, and we don't want to be overtasked with meetings. And so the next steps for our working relationship together, actually I'm super happy to announce that Laura just built the mobile app version of the new home onboarding flow. So if you could please give her a round of applause. She just launched that today, so that's really exciting.
And we worked with Teresa to figure out ahead of time again what things we wanted to track so we could make this mobile launch a success.
So thank you all, and we welcome your questions if you want to get in touch with us. Thanks.
Great, thanks. It's really exciting to see all those percentage of increases through these really small but large, in fact, findings. So next, we will welcome Josh Bloom. Josh Bloom is responsible for establishing, driving, and communication the overall technical direction for Wise.io. Wise.io is a machine learning applications company recently acquired by GE. Josh is also a professor at University of California, Berkeley, where he teaches astrophysics and Python for data science. Josh has been a Sloan Fellow, Junior Fellow at the Harvard Society, and Hertz Foundation Fellow. He was recently named as Moore Foundation Data-Driven Investigator. Josh has published over 300 referred journal articles, and in 2010 was awarded the Pierce Prize from the American Astronomical Society. Josh holds a PhD from Caltech and degrees from Harvard and Cambridge. He serves on the Berkeley Startup Cluster Advisory Committee. Let's welcome Josh.
Well, thanks so much to the organizers for the invitation. GE is the opposite of a hyperscale company. Let's get that straight from the beginning. But they are doing something very interesting. They're trying to transform themselves. They're 125 years old this year, and they're going through what they call the digital transformation. Anything that spins and is big and your life probably depends upon at some point in your life, GE makes. And they've been doing that incredibly well for a long time, but they understand the importance not only of digitization of these very large analog devices, but also the software stack on top of that, the analytics stack on top of that, and machine learning, in some sense, is the last part of the data product journey that they're undertaking. So their purchase of my little company, Wise.io, which was doing CRM, and you would think doesn't really have any real connection, is kind of what I'll be talking a little bit about today. But I also want to give you some of the learnings that we had from ourselves as a small company as we wound up building out an AI stack around data. So very quickly, you already saw some of this in the intro from Milan. We were purchased last quarter by GE. And that was sort of part of my life. I get to talk about that all the time, which is great. But I also am a professor at UC Berkeley and have been teaching data science and Python to very large audiences for almost a decade now. So I've also got to be part of the data science revolution at the educational level. And then the research side is, in some sense, what led me to the industry, building systems of machine learning to be able to do astronomy better, I guess that's the most succinct way of saying it. So in brief, I won't go into the great details of what Wise.io does, and we still have products in the market. Effectively, think of it as AI for customer support. So doing all the things that you see on the left-hand side, intelligent routing, recommended response, et cetera, connecting into Salesforce, Zendesk, and other sorts of products to optimize and make more efficient the interactions that customers have with the companies that they work with. And we obviously see customer support as a bridge to other places within CRM. So we're serving nowhere near the scale that Airbnb is serving, something like 5 million predictions a month with low latency per large customer of ours. So it's still a fairly hefty number, and we certainly learned a lot as a small company. Just to give you a sense of kind of how our product works and how we think about it and how we frame that from a machine learning perspective, you've got interactions with customers through chat and email and web forms, et cetera. Wise is basically using the transactional engine like a Zendesk or a Salesforce, reading those, inferring what's going on in that specific case, and based on the models that are built just for that client of ours. For the ones that we're highly confident what the answer is, we'll basically answer it using the templated responses that our clients have built up over time. For the ones that we're not confident in, we will basically surface that back out to the agent on their desk to basically give them some choices of how they could respond. So from the ML perspective, this is framed as a massively imbalanced, multi-class, small data, dirty label, supervised problem for the ML folks in the room. But one of the things, or some of the things that we wound up learning, obviously, as you bring AI products to market, is that if you're going to do this in a scalable way for a diverse set of customers, you need to be able to handle the diverse ways in which support desks interact with their customers. So small companies like Twilio, which have a very small ticket volume, to very large companies like Groupon, and anything sort of in between, we had to be able to speak their language and surface products that were useful for them. That should be obvious. The other thing that wasn't so obvious when we started off, and this is part of the startup journey that everyone goes through as they build their product, is to try to figure out ways to make sure that your product is not being subversive to the very people that you're trying to help. And so minimizing onboarding risk was a very big, important part of how we actually started building our product. To make sure that we're living alongside the existing processes. So in tickets that are incoming that we're extremely confident what the answer is and the cost of being wrong is very low, we'll just automate that process. For tickets where we're pretty sure what the answer is and the cost may be somewhat high, that may be an example where we'll augment. We'll present an answer to an agent, and they can serve as the circuit breaker to make the final decision. And ones where we're not confident and it's very high risk of being wrong, like let's say somebody wants a refund request, that would be something that could still be through the manual process. And over time, the idea is that as the system keeps on learning, if you've built the feedback mechanisms into the product itself to gather the data about what actions were taken or weren't taken based on your suggestions, over time, you're going to wind up getting better and better, and you can automate more and more as the system winds up learning. And then, of course, all of you who work with customer-facing products have to think about fault tolerance. The idea that when you make an ML prediction, it can't take an action that can't be undone, and it has to be understandable by the people that are going to be using it. So giving suggestions for how an agent can respond, but then also giving them some other possibilities about how they could interact is something that we had to build into our product. I guess all the things that we wound up realizing within our company, in some sense, stem back from this paper. Who's read this paper before? Machine learning is the high-interest credit card of technical debt. Wow. Okay, so it's a wonderful paper. There's no equations in it. It's like, I think, the best machine learning paper that's been written in the last several years. And it's required reading. It's going to be on the test. So please do read this if you do anything else. This quote, I think, is just amazing, and it rings very true for people that have done anything that has to do with machine learning in production. I'll just read it. It may be surprising to the academic community to know that only a fraction of the code is actually doing machine learning. A mature system might end up being at most 5% machine learning code, and at least, oh, and that part got cut off, jeez. And at least you can do the math, 95% glue code. So this is a pretty amazing statement, and I think is the point of departure for a lot of ways in which data science teams need to interact with engineering teams, is recognize that it's not just about the algorithms, it's all about all the other stuff around that. And without going into the details of the importance of this paper, it really emphasizes the fact that there are these erosions of the kinds of sort of strong contracts that you typically like to have in a well-designed software system. And basically all of that comes down to the existence of data. That a machine learning model that you build offline and then you put in production, the worst thing that you could imagine happening happens, which is it always gives you an answer. And so the contracts that you make with the rest of your system have to be able to be, in some sense, fault tolerant to that. So again, I won't go into the details of this, but I do hope you all get a chance to read it. We kind of built our stack in some ways to at least be extremely explicit in a RESTful sense about the interactions between different parts of that stack. And this is sort of the architecture diagram that we've carried with us from the CRM world now into the industrial machine learning world. Obviously, front ends and some of these need to be embedded within systems that already exist. A middleware SDK to give you not just the ability to do transactions and have a transactional database, but also out of the box getting reporting, getting alerting, getting auditing, security, auth, et cetera, right. And doing that well is something that a data scientist typically is not thinking about in their daily activity, but an engineer and those working in the InfoSec world have to think about all the time. And last, from the back-end perspective, we've built out what we call a WISE factory, which is essentially just serving RESTful endpoints for /build, /predict, and /feedback for various different machine learning models. And all of this is sort of a multi-tenant type of architecture. What's interesting, and this is not something that I would say we designed from scratch, it sort of dawned upon us that this had emerged, is that when you look at a stack like this, it's very natural to start putting people into these different parts of the stack. And then when you think about it, you also want to create an organizational API around how those people interact with each other. And that's what we did, and that's what sort of emerged. The idea that data scientists have customers within our company, and they themselves are consumers of other parts of the product and other parts of the stack. And making sure, not that everyone can't go to lunch and be friends, et cetera, with each other, but making sure that when there are requests of different parts of the stack, that there is a formal process going forward with that, and trying to make that as tight as possible and explicitly as possible is one of the reasons why I think we did fairly well as a small company, and it's one of the things that I think GE is interested in us in bringing forward. It also allows, interestingly, the data scientists on our team to be able to push to production. So they're basically pushing new versions of Docker images into our registry. And if we've built everything well, there are guardrails that the engineers have built around what could potentially go wrong, as long as the data scientists are basically adhering to that fundamental contract of what comes in and what comes out. Okay, so transitioning a little bit, just in the couple minutes that I have left, let me talk a little bit about where all this fits into GE. First of all, the industrial Internet of Things, or IIoT as GE calls it, is not about thermostats and Fitbits and self-driving cars. It's again about very heavily connected, very large machines of very large value, where the types of problems and the types of data scales that you're looking at are not generally found in the consumer internet. So I think of this as the internet of really, really important things. From a data management perspective, a single airline engine, when it finishes a flight of 5 hours, produces about 1 terabyte of data that needs to get analyzed very quickly. From a connectivity perspective, you can imagine there are some mission-critical types of factories, nuclear power plants, that need to be online, need to be monitored all the time. From a lifetime perspective, some of these things need to last for decades, if not centuries. And security is obviously something that's incredibly important to all of you in your own worlds. But if you think about the type of data that's being produced by companies like GE and its customers, this is the kind of data that nation-state actors are trying to get access to. So having a massively secure environment and doing that well, also in the context of surfacing out data products is non-trivial. And obviously from a privacy perspective, there are massive numbers of federal regulations, at least for now, that we have to deal with. So for me, and thinking about bringing kind of a verticalized focus of AI products to this really white space world of industrial internet, comes down to this slide. It's the idea that if we can move the needle in just efficiency, let alone other potential axes of interest in any one of these different regimes, rail, aviation, healthcare, power, oil and gas, et cetera, these mean a massive amount of dollars and incredibly impactful to a large number of people's lives. As we've started building up this team, and also kind of being on the educational side of things, I've gotten to think a lot about how we're going to be teaching people and what types of people we want to bring into our teams. Now, not specifically in data science or engineering, but more broadly in a technology stack. I don't know if any of you have heard of this analogy, but many people have advocated for the idea that we need pie-shaped people. Has anyone heard of that before? Okay, well, yes, okay, we've got one person in the back. So this is the idea that you need to have somebody who's incredibly deep in their sort of domain, but then also incredibly deep in, let's say, computer science or in statistics. And there are a lot of people who go around saying, this is how we have to teach people. I actually think we need to teach people and work with people that are what I call gamma-shaped. The idea that you're incredibly deep in something and you are the world's expert or becoming the world's expert in something that is of value to the company that you work in or in academia, but you know enough about other fields that you can work with those that know something a lot different than you, other gamma-shaped people. And this is all basically that statement that data science is not done by a person, it is done together with other people, and with engineering, it's really a team sport. What I'll end with is to say that what we were able to do at WISE is obviously very small in scope, sponsoring events like Women in Machine Learning, recognizing that diversity isn't just in what you know, but also your backgrounds. And we've been able to work with some really wonderful women over the years. What I'm incredibly excited about and very proud of now being part of GE is this initiative that GE came out with just a month or two ago, the idea that they're going to be hiring another 5,000 women in STEM. They're now at about 15,000, and they're trying to get to 20,000 in just about 2.5 years from now, and to try to get 50-50, so parity representation of all technical entry-level people, so have a gender balance there. That's what they're striving for, and I'm extremely excited to be part of that journey. So a little bit of an advertisement for a conference which was going to be held in Vegas in the middle of the summer, which is not the ideal time to go to Vegas, but is one that we're excited about, Industrial Machine Learning Workshop. It looks like it may actually be postponed, and we may hold it in San Francisco in the fall. So please keep your eyes out for that on the Twitter spheres. And with that, I'll say thanks, and of course, we're hiring. Thank you.
All right, we are halfway through. Oh no, we have 2 more talks coming. Okay, more than halfway. Hope we are still in good shape now, or stretched a little bit. All right, so next we have Evelyn Shen and Cookie Perez. Evelyn is a software engineer that has been working with us for 2 years at Airbnb. Cookie is a data scientist and manager at Airbnb. She has been with us for almost 2 years. Prior to Airbnb, she was a professor for 3 years. And before that, she got her PhD from Stanford. She is originally from Chile. Let's welcome Cookie and Evelyn.
Hello. We're almost there. 2 more presentations. My name is Cookie. I'm a data scientist manager here at Airbnb. I've been working with Evelyn actually for the past 2 years, and we have been building product for our host. We actually also worked last year with Teresa and Laura, so I guess our team is the one where we actually collaborate between data scientists and engineers. Today we're going to share actually how we work closely, how we collaborate, and we're also going to talk a little bit what happens when you don't collaborate, and it's kind of like, not that happens to us, but also we will give some example of that.
Well, I once got an advice. It says, ask your interviewer where the data scientists sit. If they don't know, run. I think it's also true vice versa. If you are a data scientist and your interviewer doesn't work closely with their engineering partner, you probably want to think twice before you join the team.
Excellent. So the outline of what we're going to talk today, before I tell you what we're going to say, is actually when you think about collaboration between data scientists and engineers, you immediately think machine learning algorithm, data product building. Like actually, even when I Googled in preparation for this talk, that's all I could get. It's hard to find actually how do data scientists collaborate with engineer when you're building product, when you're in a product team, and how is it that you can actually be working together? So in our presentation, first we're going to talk about how important that collaboration is. We're also going to talk about what happens when you're not collaborating, and which is not unusual. And then we're going to talk about how good it is to collaborate, and we're going to give 2 examples and some takeaways.
So at Airbnb, we say one team, one dream. As a team, we want to focus on building high-impact product efficiently. To achieve that, we need to measure impact rigorously and iterate fast.
So as data scientists, when you work in a product team, you're charged to deep dive on the data, get insight about user performance, and basically use those insights into our roadmap. We are also charged to measure the team impact. We need to come up with metrics, how we're going to attribute our efforts. And last, we are also responsible for setting up our A/B tests in a very rigorous way, and also making the final call if we should iterate or launch or not a new product.
Well, as engineers on a product team, we aim to make best use of the infrastructure we set up so we can take insights from data scientists to production quickly. And we also want to make sure the right data is being logged and stored for easy retrieval so data scientists can get the data they need when they use the data.
Excellent. So this is how it looks when there is no collaboration. So imagine data scientists and engineers working totally on isolation. So there you have the data scientists using the company data, using result of A/B tests, doing analysis, and start finding, oh, there's so many data inconsistency. Oh, we don't have the data that we need. I don't have the right data log, so I cannot do an analysis. I may be also focusing on the wrong question. I think this is very important, but it's like engineers or nobody else in the team actually care about that question. You end up, you're very proud, you publish in this company what we call a knowledge post. So it's a beautifully peer-reviewed knowledge post, but actually nobody cares about it. Nobody reads it. It doesn't inform your roadmap, and you're done with your work.
Well, when there's no collaboration on the side of engineers, we don't know what informs the product decision. We're not sure about the hypothesis behind the product we're going to build. And when we build the product, logging is mostly for monitoring the system healthiness rather than for the analysis. Without a clear underlying hypothesis, A/B tests now turn into a process almost like, let's put the changes out there and see what happens.
Exactly. So when the system is broken, when there's no loop of collaboration, data scientists are publishing their knowledge posts, and those are not actually informing anything that is happening on the product roadmap.
And there's always gap and inconsistency between the production data and the analysis data. Data scientists cannot do their analysis very efficiently, and engineers build their product without confidence. The truth is, we really need each other.
Exactly. So why data scientists need engineers? So data scientists are really good at knowing the data they need and the data that we have right now in place. We're very proficient at using R, Python. We can clean, manipulate, do analysis. We can model the data. We also are very good at coming up with experimental frameworks that will allow us to test very rigorously if the feature that we're implementing is actually having an impact. But where we benefit a lot from collaboration is, as I said, we really need high-quality data for our analysis, and we need the right data. We need to make sure we're logging the right information. We also, data scientists don't like to do one-off project, one-off analysis. And if you're not collaborating with your engineer, it's really hard to actually automatize your analysis, have the right pipelines, have the right dashboard, so your whole team can be data empowered.
Well, why engineers need data scientists? We have a lot of hands-on details about the data, and we're at the position to ensure consistency and standards for loggings. Our tools is mostly for a scalable system, and we are good at taking the one-off analysis to scale them into data pipeline and dashboard. But the engineering systems are expensive, so we really want the data insights to get the product decision, and we need data scientists to give us the methodology to test impact and inform iterations.
So when we collaborate well, actually, this is when that's what we call it, this closing the loop. We can see, for example, data scientists will do an analysis, and this time they will have data that has no inconsistency. We have the data we need. We were logging the correct data. We're actually focusing on the right question. And all of those we can inform if we need more data, if we need to improve our logins. And then the team is going to be much more empowered with the right logins and the right pipelines and dashboards.
With data-informed hypothesis, now we get more confidence in the product directions, and we have clarity around the data we need to track so we can come back and verify the hypothesis. When engineers build the product with these in mind, we can put the logging in place both for monitoring and also for analysis. We keep the analysis data consistent with the production data, and we ensure the right data gets to the data scientists for analysis.
So as you can see, when we are collaborating, we're actually building product that may have a very high impact. Data scientists are focused on the right question, and we actually have the data we need to be doing our analysis.
Well, now we're going to share with you 2 examples of our collaboration. When we're facing a brand new problem to solve, how we work together to build a good data foundation and set the team up for success. And when we're at the stage of iterating a product, how we work together to build a great product.
So we're going to start with when we have a team where we're working on a new problem, and it's usually how good it is to collaborate with engineers, data scientists, to have a very good data foundation that will set the team for success. So imagine we're focused on a new problem. We're thinking, what do we do? So data scientists usually will go deep dive and try to get insight from the data. We're going to start learning the behavior of our users. And we may come up with some ideas, some features that we believe we may experiment or implement in our product.
And engineers have all the knowledge about the details for current status of product. And they also know the feasibility of the features we can build. Combined with the opportunities explored by data scientists, we're able to come up with buckets of levers and projects we can build.
Excellent. So once we identify those buckets of projects and levers that we're going to be focusing on, usually data scientists also need to be focusing on what are going to be our goals, the OKR, how we're going to measure those, attribution, but also in collaboration with engineers, we're going to be thinking, okay, what new data do we need? What new pipelines, dashboard do we need to build in order to start tracking our efforts?
Well, engineers will work with data scientists to implement the new experiment framework, identify new metrics and data to track, and we can also work on metrics cut so we can automate the analysis. Well, next, we're going to share with you an example when we're coming to a more like iteration stage of the product, how we build a good product together. This is the product we used to ask hosts to upload photos for their listing around a year ago. And this is what it looks like today. So how we got from the left side to the right side.
So data scientists, we start immediately looking at a funnel analysis, very similar to what Teresa was describing, and looking at which are the areas where we see a big drop-off of users, for example. We found that uploading the photos, it was actually a big drop-off point. We also realized, given that it was a big drop-off point, the immediate conclusion for you is to say, well, we need a bigger and better call to action. But we also realized we only had impressions of the page. We didn't have anything about clicks, quality of the data, photos, etc.
Well, take that insight from data scientists. We built this iteration where provide a much clearer call to action and encouraging messages for hosts to upload photos. At the same time, we also put the logins in place to track user interaction and have much more information about what type of photo and what kind of files they're uploading.
So in the meantime, when we're doing this iteration on that step, data scientists are also doing some analysis. That's how our knowledge posts look like, very similar to a academic journal paper, and there's where we are actually publishing the type of analysis that we're doing. And we were finding, for example, the high quality photo, like professional photography, was very important for new listings. We were also looking what does it has an impact on the probability of a new listing, getting a booking. We realized the quality of the photo, particularly the cover photo, was very important. And we also got information about the type of photos that users are uploading. Some of our users were actually using our mobile device.
Well, because your camera is on the mobile, so a lot of people are using their mobile devices to take the photo and upload from there. So we did the second iteration, which is redirecting hosts from the web platform to their mobile devices so they can take photo there and upload from there. And at the same time, we also keep track of the user interactions and the data, and we have some new findings.
So we also deep dive there, and we explore and look at we did convince some people to actually move to mobile to upload their photos, but conversion actually on the whole step didn't increase. We also find out that the quality of the photo was going down because now more people were using their not so good mobiles to take the photos. And the only good finding was like, well, people are taking a shorter time, that's it.
So with all the iterations and data insights, we realized, well, the uploading flow is very important, but the quality is really the key. So we come down to our final product where we provide a quick upload flow and early preview for the photos. Hosts can easily see how guests view their photos, and at the same time, we provide a tool for them to improve the quality of their photos.
Exactly. So given that we had found that at the end of the day, it wasn't so much about like getting the photos up, it was we need very high quality photo. Building that feature was really key. And we did also improve the % of people that were actually converting and finishing that step. So a couple of takeaways.
First of all, and most importantly, we have the co-ownership of problems. So data scientists and engineer on the team align on the vision of the team. We both fully committed to the delivers of the projects, and we align on how team success should look like so we can very well measure the progress and iterate fast.
The second one is that we actually need to be working in a very synchronized way. So data scientists can help you unpack what's happening with your users, can give you and provide data insight that can inform your data roadmap. Engineers, on the other hand, can help you understand what data do we have, what is it that we're collecting, how do we need to modify that. And last, we can help one another actually understand if the new features we're planning and implementing, do they have potentially a good potential impact, and also how feasible they are to be implemented.
Well, with all these alignments and shared understanding, we're able to amplify each other in the decision-making process, so we both influence the product directions.
Excellent. So basically, just to summarize, particularly being two women in a data product, in a product team, I think once you have co-ownership of the problem, you work in you synchronize the work, and you amplify each other is when you actually end up being 1 + 1 is greater than 2. And that's our goal. So thank you.
Thank you.
Thanks, Cookie and Evelyn. Great talk. And we are heading to our last talk from Andrew. Andrew is an engineer at Hotwire for 2 years. She's mainly working on search and pricing. She's a back-end engineer, and let's welcome Andrew.
Hi, everyone. So this is going to be the last talk. I'll keep it short, I promise. So the main topic of my discussion is going to be how we are collaborating with our data science team in our microservices environment for Hotwire. So in Hotwire, I work as a backend engineer in search and pricing team, and we are actively working on solving a problem that is to disintegrate our legacy system into smaller, more manageable microservices. So we have a really huge legacy system, and it often becomes really difficult to iterate upon this particular system, and we want to be able to iterate on different aspects of our search and pricing flow in order to improve our conversion rate. So the approach that is taken by the technical leadership team is to go towards the microservices architecture, And let's just go ahead. But what are the advantages that we get by going with this route? So this definition of microservices by Martin Fowler is sort of what I can actually relate with. There is no set definition of it, but to me it just means a bunch of services which are built to fulfill certain business logic, and they can be iterated and improved upon independently. They are loosely coupled from each other, and they have their own release cycles. So this is basically what microservices mean to me. So why are we going the microservices route? So we get a lot of standard benefits by following this approach. So first is scalability. So microservices are typically deployed within cloud, and it is very easy to scale up or scale down in a cloud-based environment rather than being in a traditional data center. So our current legacy system is residing in a data center, and we want to move away from that. We want to take all of our search and pricing logic into AWS and basically use all the out-of-the-box solutions that are provided by AWS clusters. So, so scalability is pretty important. We have different demand based on different times during the day, like the traffic can go up, go down. So we need to be able to scale up and down based on how much traffic we are getting. Another advantage that I see is maintainability. Legacy system is pretty hard to maintain. It is often very difficult to troubleshoot any issues that we find in production in a legacy system. However, if it is a microservice, then it's pretty easy to find out where the problem lies. So, and also microservices are pretty smaller code base, so they are pretty cleaner. We can design our code in a way that it is more readable, and build and deployment pipelines are most of the times automated completely. We make sure that we have enough test coverage, and that sort of ensures quality and maintainability. And also, we work in agile environment, and that means that teams and folks in the teams, they move around, and we often end up inheriting other people's products. So when that happens, if your code is not good enough, it kind of becomes really, really difficult to get up to speed on the new product that you have inherited. Like from my example, I inherited pricing, and earlier I was just part of search, but then I inherited pricing, and it was pretty easy because pricing was already migrated into a microservice. So it was pretty easy for me to get up to speed on pricing. So maintainability, I think, is pretty, pretty important from my experience. Then clear separation of concerns. So this sort of kind of goes hand in hand with maintainability, but in search and pricing, there are some very distinct steps, and they can all be separated out and iterated upon by the product team. And separating these out clearly is one of the advantages that we get by converting our system into smaller microservices. Loose coupling, all the services are going to be independent of each other. They are going to have their own life cycle, release cycle. They are also going to be independent of the monolithic system, so definitely not tied to the monolithic system's release cycles. So loose coupling is pretty important. We are an A/B test-driven company. We do A/B tests pretty often, and that means that we want to ship code to production pretty often, and it becomes really hard in a monolithic system to achieve that. So easy and faster iterations is kind of similar to what I said just before. And obviously, we have very short build and deployment cycles. For monolithic system, traditionally, like if everything is residing in one code base, just imagine how complex the release and build and release cycles are going to be. Like release times will probably be like hours, maybe. But with microservices, we can reduce that to just a few minutes. And also, one important thing I wanted to highlight, I don't know about other teams, but at least in Hotwire, we have a centralized release team, which is responsible for managing release cycles of the monolithic system. However, individual teams that are building their microservices are responsible for their own release cycles. So it's continuous integration and continuous deployment is kind of ownership of the engineering team. So these are some pretty great advantages of microservices. I want to move on. So at Hotwire, I just want to quickly talk about how a hypothesis turns into a product. So the very first step, or there are several different steps in how a new product gets evolved within Hotwire. So microservices and all is all great, and this is all from the perspective of technical roadmap. But there, we also have a product roadmap. So if you want to make sure that we are in line with delivering on different deliverables or different KPIs with respect to whatever product roadmap that we have. So we can't just pick a certain business logic out of the search and say that, okay, let's move that into a microservice. It's probably not the best way to utilize our time, and we want to make sure that we are actually delivering some business value as we move our legacy code base into a microservice. So the very first step is to propose a hypothesis. So this analytics and data science team and even engineering, they can propose some hypothesis which is in line with the product roadmap. And obviously, the hypothesis is often backed by data. And after a hypothesis is proposed, the product team prioritizes it, and we want to run a very quick A/B test just to get some signals on that hypothesis if no other test has been done for that hypothesis before. So this is where the engineering team is it steps in, and along with the data science team, we find a quick way to get some significant customer signals by quickly implementing an A/B test. So this does not necessarily mean that we are going to move this logic into a microservice and then test it out. We can just leverage the existing system that we have and implement a very quick test. And once that test hits production, the analytics, engineering, and data science keeps an eye on very important metrics that drive our business. So for example, we want to make sure that we want to keep an eye on our conversion rate. We want to keep an eye on our net promoter score or the post-booking score. We want to make sure that our users are happy or not happy. Both the signals are equally important. So once we get some strong signals from the user, we basically decide that this particular feature is worth iterating upon further. It can actually generate some revenue for our product, and it is definitely worth investing time in building a more scalable solution for future iterations for this particular hypothesis. So the next step is to productize this feature. At this stage, the engineering and the data science team, they kind of get together, and we basically discuss and collaborate on the design decisions. So most of our search and pricing logic is based on machine learning models, and pricing is extremely sensitive, so is sorting. So we got some very clear signals that as soon as we mess with these two aspects of search and pricing, we see some very strong signals, and then we decided to turn it into a microservice. And then the data science team kind of sits with engineering, and we come up with we come up with the design of the new service. We decide what kind of data we want to send to the new service, what kind of data, what kind of features will be used to develop the new models for our A/B testing. So once the feature is productized into a new service, or it can also be added to an existing service, it really depends on what the hypothesis is that we have tested. Once we do that, then again, we basically run an A/B test for the new models that we have built. And we also implement logging framework so that we can aggregate data for training those models that we have just built within the service. So these are high-level stages of testing a hypothesis and building a product. So I just quickly wanted to show like what kind of architecture we are having currently. We have a really giant legacy system out of which we are trying to improve search and pricing algorithms based on machine learning models. So the cloud has several different microservices. I have listed out 2, but then there are, within search, there are so many different things that happen, like the user enters a search string, and then what all neighborhoods get picked, based on that search string, how we are selecting our hotel and car inventory. There are so many different things that go on. So I have listed out scoring is basically the last step. So this is like based on whatever results or hotels that we have selected, how we want to score them. So scoring services job is that. Pricing service is basically pricing all of those hotels, and there are there are various different machine learning models that are running. And we are also building, we also have an S3-based, Kafka-based event logging system that essentially dumps data into S3. And from there, the data pipeline is basically extracting this data from S3 and other ETL processes which reside within the legacy system. And that data is then used to train the models that are running in scoring and pricing service. So in terms of the incoming traffic, we have native apps, web, and MWeb clients, and the search request initiates from these 3 different clients. And we have an A/B test framework which basically decides in which A/B test bucket for all those different A/B tests that are running, it is going to fall into. So an individual request coming in, the A/B test framework will basically decide if it will execute a particular model of a scoring service or use a certain model of a pricing service. So there are several different models running within scoring, pricing, and other microservices. And the A/B test framework sort of determines in which bucket the search requests are going to fall in. So that is the overall architecture of how we are A/B testing currently. So a very specific engineering team's role is to A/B test the hypothesis in a quickest and cheapest way to gain some customer signals. Once we have some customer signals, we architect a new solution that we want to move out of the legacy system into a new microservice. So this is not just the feature, but the entire logic around that feature, which relates to that feature, which makes sense to be part of one service, is moved out of the legacy system. And once we move this out, we are also responsible for automating our build and deploy pipelines, and also automating all the functional and unit testing and performance testing frameworks. So after the services are built, obviously the engineering team is responsible for operational support and maintenance of the services, and building data pipelines for our data science to train the models that are running in microservices. So I'm going to quickly give an example of scoring service. This is the very first microservice that we built within Hotwire about a year and a half ago. This was the very first time we actually proved out that this kind of framework is going to work for us and is going to help us generate some revenue. So basically, the hypothesis was that the conversion rate or the purchase rate for hotels at the top 5 or 6 positions is more than the others. So we wanted to test out this hypothesis. So the very first thing, we did not have any service, we did not have any infrastructure. We just had the legacy system, which was running within our data centers. So the very first thing that we did was to build a very, very simple model, which was just a very simple logistic regression model, just to test out if we change the sort order of our results, how do our customers react? And when we did that, we saw the needle move pretty drastically. We saw that there are some very significant changes to our user behaviors. They were scrolling down more, scrolling down. The hotels that would convert earlier would not convert anymore. So we were getting some very strong signals, and we knew that sorting is a very important part of search, and we want to invest heavily in that. So we built out this scoring service infrastructure, which is basically, we started from scratch. We built a cluster we spun up a cluster within AWS. We built our own internal Docker registry. The data science team wanted to, so basically they were more comfortable with using Python for developing their machine learning models. So we built up a Python-based image, which was pushed into the internal Docker registry. And this was like a one-time thing, so all of the dependencies that were required for building or implementing the models were pushed into that Docker registry. And, excuse me. So once that was done, then we basically built a RESTful API called Scoring Service. So it's built in Python. And we sat down with the data science team, and we decided what kind of request or response structure is going to be. What all data do they need in order to score them for their models? So they started off with some very simple models initially, some very simple linear regression model, and then later on moved on to random forest and BDT models. So so basically, they built the models, and then it was the job of the engineering team to integrate those models within scoring service. So hypothesis was the first step. Implementation was the next step. And after that, engineering has been involved throughout this, but then the clear handoff happened after the models were implemented, and it was time to integrate them within the scoring services code base. So this is just basically done via a pull request. So once the data science team is done with building the model, they built out a serialized machine learning model file. It's a pickle format, and it gets integrated within our scoring service via a pull request merge. And when it gets merged, we just start off our deployment pipeline, which is completely automated. It has all the necessary test cases and performance testing, and everything is automated within the pipeline. If there are any issues in the pipeline, we collaborate with the data science team to fix those issues. Sometimes we see some resource utilization issues, such as higher CPU utilization or memory utilization. Then we try to optimize those issues. We see if latency has increased, because search is very, very latency sensitive. So we want to make sure that our latency metrics are maintained. We don't add more time to our search. So we work with them in order to optimize if there are any issues. And once the deployment is done, then this engineering team is responsible for supporting the service in production. So whoever we have on-call rotations, if there are any issues, we take ownership of that. So this kind of collaboration has worked out really well for us, and we have definitely gained a lot from this kind of a framework, and we want to continue to use this for our other aspects of search as well. So we are almost done with ranking and pricing, and now we want to move on to some other more subtle aspects of how we select our inventory, what kind of neighbors we want to select. Depending upon the time of search, we want to make sure that we select the best neighborhood for our users, so that they end up having the best travel experience. So I think data science and engineering are very, very essential to search and pricing and pretty much entire product development. And I think one cannot do without the other. Thank you.
All right, thank you. So let's have our speakers step up on the stage, and we'll take a quick couple questions, and then because we are already around over time, so we will try to wrap up by 8:30. But let's just take a couple quick questions from the audience. Anyone?
Hi. You keep saying you optimize for metrics, but how do you choose these metrics, and what's like the overall goal that you try to optimize for?
I'm a huge fan of the hierarchical approach, where you start from the top down, understand the vision of what you're trying to build towards, and if you can measure that, great, start with that one. Move down to, okay, these are the main components that will help you build up towards that vision. At this point, you may be saying, okay, the vision of Pinterest is to get discovery for every idea in the world. If you can make change on that, great. But the next layer of metrics under that is, well, I can make change to the search metrics. I can make search more efficient. So you have the search metrics, you have the discovery, you have the P2P, and underneath that, you have the operational metrics of, did I make search faster? I may not have increased precision or recall, but if I increased speed, that's a step in the right direction. So hierarchically build your metrics up from the vision that you want to get to, the product level of, these are the strategic ways to get to that vision, the operational layer of, I can execute on that strategy quite well, and down to the baseline where you're moving things on a bit-by-bit basis.
Thanks.
And I'll just add a little more specificity to that. So Airbnb, as with any hotel, we want to book nights. And so from the supply side, we have a machine learning model that estimates the lifetime value of a piece of supply based on how it was, if it was added, if it was published, and it was booked. And so our metrics fall out directly from the overall goal of nights booked, translated through this machine learning model to value a unit of supply.
Do you also value a unit of demand? Do you try to figure out what your customers are worth? And do you do differential pricing according to what they're willing to pay, as demonstrated by past behavior?
We as a platform don't do any sort of enforced pricing. The supply side is always in charge of setting their price, but we do have a model that is designed to, that is just ramping up actually to estimate the lifetime value of a unit of demand.
But do you offer people more expensive properties if they have proven they can afford it?
No.
No? Okay.
Hello. I think it was June who mentioned about documentation and kind of adding decorators to auto-document. And there's this maxim that says, by the time your documentation is fleshed out, it's deprecated. And yeah, there's a lot of tension between ample documentation and deprecation of documentation and maintaining that documentation. Thoughts?
The one thing I'll add to that, we didn't get to that, is that when you're doing your documentation, you're measuring the quality of your data, you're going ahead, you're writing your workflow for calculating it. It's one step further to automate that so it's happening inside a dashboard on a daily basis. So at that point, the documentation becomes colloquial knowledge, your tribal knowledge, written down with a link out to your dashboard that it's updating on a daily, hourly, however frequently is pertinent to that data, so that your documentation is your glue and not your bricks that are necessary for every day to day.
Only one protest, and that's just, isn't that supposed to be the tests? Isn't that what the tests are supposed to be?
Tests can help you with guidelines, and certainly getting to a point where a unit testing for data is standard. I would absolutely love to be there as a field.
Me too.
We'll get there.
Hello. I had a question, like you described pretty well the interactions between engineers and data scientists. How do product managers and designers come into play?
No, this is just a team of engineers and data scientists. Of course, they're a big part of the play. I think, as you probably know, the product managers are the ones that are actually enabling this communication between engineers and data scientists and designers. And also, we also have another player in this group, which is at Airbnb's researchers. They are what I see them more as like the more qualitative researcher, like the one doing the user testing, and also many times helping when I said that data scientists at the beginning explore the data, try to get user behaviors and insights into into the roadmap, we also work closely with researchers. Designers, of course, are the ones that are going to do the magic at the end of all these ideas that we have. And the product manager is the one that is enabling all of this to happen. But yeah, it's all of us. Yeah.
I forget which one of you guys presented it, but one of you guys had a slide around a dashboard that basically had like one row per metric, and on the far right side you had the minimum detectable effect for each metric. How do you go about deciding whether you want to see a 2% or a 4%, or how do you decide what your minimum detectable effect is for each one of your metrics?
Oh, so it's calculated on the fly based on sample size and sample variance. So there's a calculation you can do to get to minimum detectable effect by choosing your power. So we typically use 80% power in that dashboard, and it's recalculated every day based on the sample size that has been taken in now. So that is the current minimum detectable effect, and we actually, if you click into it, there would be a graph that would show you, well, if you let this run 10 more days, here's where we predict your MDE would be. So that is the, at that time, not sort of what we want it to be.
Cool.
So looks like we have answered all the questions. Great. Really thank you for coming today. It's really great to see so many people in the industry working on similar problems, and we have a venue to an occasion to discuss all these exciting problems. The speakers, if you are interested, we are happy to facilitate you to talk to these speakers as a follow-up conversation. But now let's thank the speakers again, and thank you for coming. Thanks for having me.